Hello friends, hope you're doing well. In this video, we'll go over the second example from the topic of degree of indeterminacy and stability of structures. This example is from December 2018, and it was question 1. If you remember, we said that the degree of indeterminacy for beams and frames can be calculated using the formula 3K plus R, 3 plus C. Where K is the number of closed loops, R is the number of support reactions, and C is the number of constraint equations. The number 3 is because we can write 3 equilibrium equations for the whole structure. As you can see, this question 1, part A, is almost exactly the same as part A of the previous question from the last video. In fact, if you look at other questions from other years, part A is always something like this, with only a very minor change. So if you pay attention to this pattern, you'll be able to solve part A quite easily. Now, for the support reactions, we have 1, 2, 3, 4, 5. That's 5 reactions. 0 closed loops, minus 0, plus 2 equals 0. This is a determinate and stable structure. We already discussed this in the previous video and confirmed that this part is stable. We'll now analyze this section and see that it's also stable. So, this structure is determinate. In the next example, as you can see, we have 3 reactions here and 3 more here, making a total of 6 reactions. No loops, and 1 constraint equation. So, n equals 3 times 0 plus 6, 3 plus 1, equals 2. That means this structure has a degree of indeterminacy of 2. Alternatively, instead of analyzing it like this, we could separate the structure and draw it like this or like that. When we do that, these are our support reactions, and these are the internal joint forces. These are the forces acting at the internal joint. If we count the unknowns, we get 3 here, and 2 more here. That's 8. And the number of equations is 2 times 3 equals 6. So again, 8 minus 6 is equal to 2, meaning the degree of indeterminacy is 2. So, this structure is indeterminate. As for stability, it's obvious. This section has proper supports, and so does this section. They are connected by a single pin, and if we connect it at this joint, it's clear the structure is stable. In the next example, as you can see, there's 1 loop, three reactions here and 3 reactions there. So, n is equal to 3 times 1 plus 6, 3 plus 4, equals 2. How many constraint equations do we have? 1 for this joint, 1 for that, 1 for this one, and 1 more, so 4 in total. Again, the result is 2. Now, we could separate and analyze this again, but the important thing is that from a stability perspective, this part of the structure is stable, this part is stable, and it provides proper support for this section. So, the entire structure is stable. Now, if we want to analyze the external indeterminacy using the separation method, we can see that we have 3 reactions here and 3 there, that's 6. Then, 2 here, 2 here, 2 here, and 2 more here. 4 times 2 is equal to 8. So, 8 plus 6 is equal to 14. 1, 2, 3, 4. So, 3 times 4 minus 14 is equal to 2. Again giving us a degree of indeterminacy of 2. So this is also an indeterminate structure. The next structure is very simple and clear. N equals 3 times 0 plus 4, 3 plus 0, equals 1. So our structure is indeterminate with 1 degree. Why is it indeterminate? Because of this support. If it were a roller support instead, the structure would be determinate. We're analyzing a solid body in terms of stability. The body and its supports are clearly defined, so the structure is stable and indeterminate. Also, keep in mind that we're not considering the loads on the structure here, because when analyzing stability, we're only concerned with the structure itself. A structure should maintain stability under any loading condition. If we can find even one counterexample where the structure loses stability, then the structure is considered unstable overall. The next example is a truss structure. We use the formula N is equal to M plus R minus 2J, where M plus R are the unknowns and 2J are the equations. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 members, plus 3 reactions, minus 2 by 7 joints. 1, 2, 3, 4, 5, 6, 7. So the structure would be determinate, if it's stable. Now let's check the stability. We should see if our structure is stable or not. If you pay close attention to here, we have a triangle here, a rigid body. We could start from here, 1, 2, 3, 4, 5, and like this. I might have made a mistake. Let me check again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Sorry, there are 12 members, plus 3 reactions, minus 7 joints times 2. So, N equals 12 plus 3 minus 14 is equal to 1. So the degree of indeterminacy is 1. For stability, we can say this is a stable part, this is also stable. And this one is stable too. So we have three stable structures here, connected via two joints and two members. Without member number 3, stability would still be maintained. But since member number 3 connects these stable segments, it adds 1 degree of indeterminacy to the structure. So because of the structure number 3, our structure is indeterminate. In the last structure, again we use n is equal to m plus or minus 2j. Let's count the members. 1, 2, 3, 4, 5, 6, 7 members. Plus 4 reactions, minus 2. The reactions. One, 2, 3, 4, 5, 6. By 6 joints. That gives 7 plus 4 is equal to 11, and 2 times 6 is equal to 12, so n equals 11, 12 is equal to minus 1. Since the number of unknowns is less than the number of equations, this is an unstable structure. Thank you so much for watching. In the next video, I'll go over another example from past questions related to stability and indeterminacy. Thanks again, goodbye.